Hey everybody, thanks for showing up. I'm Jonathan, this is my coworker Dave. We are here from Hinge and we're gonna talk a little bit about how we apply Ray for our machine learning use cases to accelerate our time to production. Really fun stuff. So just to give a real brief intro to all of us, my coworker over here is Dave. He's a great guy. Go talk to him afterwards. He works on a team within Hinge called Dating Outcomes. Dating Outcomes basically is responsible for making sure that Hinge, the app is doing its job and helping people find their best matches on the platform. Previously, he worked at health tech, and before that, he was a PhD candidate at the University of Michigan, and he likes astronomy, the ocean, and data-driven decision making. Meanwhile, I'm also at Hinge, obviously, but I work on a team called AI Platform Core, and this is the team that's responsible for basically platformizing our approach to machine learning so that it generalizes across all use cases and teams within the company. Previously to this, I worked at Spotify also on the ML platform, and then before that, I was at NVIDIA and Twitter back when Twitter was still Twitter. Outside of work, I spend a lot of time playing video games and all that fun stuff. So let's do a bit of an overview about what we're going to be exploring today. I will give you a bit of an overview of Hinge, the company, and also the role that machine learning plays within the company. And then we'll switch things over to Dave, and Dave will kind of give you the full rundown of our architecture. He'll give you the backstory of things, where Ray sort of came into play, and at the same time, how we're leveraging Ray for our use cases today. And then we'll close things out with kind of a preview of how we at Hinge sort of see this platform and infrastructure growing alongside the company to help it achieve its goals. So let's get started. Hinge, for those that might not be aware, is a global online dating platform. It is owned by the Match Group, which also owns Tinder, OkCupid, and a handful of other companies as well. It is a very well adopted app and platform within its target markets. We currently sit at about 10 million MAU as of Q1 of this year, and we are one of the top 3 most downloaded apps within all of our target markets. So specifically, let's talk about machine learning at Hinge. Machine learning at Hinge consists of a fairly small team of about 20 members last I counted, but these members are split up across basically 4 teams. We have what I think of as the three focus areas within AI and ML at Hinge. First off is Dave's team, Dating Outcomes, which I gave you a bit of a description of previously. We have another team called Trust and Safety, which handles protecting our users to make sure that the platform is safe and enjoyable to use. And then lastly, we have a team called Growth, and that is responsible for user acquisition and retention. Sort of underpinning all of this is my team, the AI Platform Core team. Like I mentioned previously, we are responsible for building out the common tooling and the foundations that help all three of Dating Outcomes, Trust and Safety, and Growth to achieve their goals. Some of the recent work that we have put out that's available on Hinge right now. The first one is a feature called Top Photo. Basically, this leverages a computer vision recommender model to dynamically sort the photos on a user's profile to make sure that the first photo that people see when they view your profile is most likely the one that best represents you as a user on the platform. The second one I will talk about a little bit is harmful content detection. Basically, the idea that it kind of builds on the idea that detecting a message that's harmful after it's sent is only half of the solution. It's far better to detect the message before it's even sent in the first place. So we use a machine learning model here to process messages before they're sent, and if they are detected as containing disrespectful or potentially harmful language, we will prompt the user to reconsider the message that they're about to send. So now this is the time where I'm going to swap things over to Dave, and Dave is going to give you a rundown of our architecture.
Thank you, Jonathan. All right, so I'm going to jump right in. With a bit of background. So let's start with a brief overview of where we were a while back in terms of an ML platform. So we use Spark for distributed computing, and specifically we use the EMR platform to manage this for us. So this was a tricky platform that slowed us down quite a bit, and the overall development was quite unergonomic. So this picture looks complicated, it's meant to, right? So we kind of faced a bunch of challenges. We couldn't update Spark versions in our own cadence because this is something that EMR managed for us. Logs appeared every 5 minutes. It was written on S3. We had to kind of get it out of there to read them. Submitting applications involved physically copying it to S3, pointing EMR to it. And then finally, Spark is not designed generally for GPU computation. So these are kind of the things that we were up against and then led to a desire to upgrade our platform. So over time, we decided there's a big push to A, bring deep learning to our recommenders, and then B, come up with a platform that actually supports this. So Ray was a clear choice. It's Kubernetes native. It snaps to the rest of the tech used at the org. All our microservices are on Kubernetes. It has great out-of-the-box monitoring, so Prometheus, Grafana. It's Python native. We can actually view and understand the logs we get. And it's easily customizable, so we can change the Python versions, the packages, wherever we want, as we please. So before we kind of did this, right, what are the goals and the things we want out of a platform like this? So first thing is feature-rich, right? So we want a solution that has monitoring, logging, CI/CD, right? Previously at this venue, we've seen a number of solutions that are bespoke. So they provide thin layers around Kubernetes, for example, and because they're bespoke, they become very customizable. But for us, as Jonathan mentioned, we're a relatively small team, at least to start with. And at least in the beginning, we'd like to focus on A, modeling, and then B, kind of more platform components like feature store, serving platform, et cetera. So to start with, at least, we chose to focus on things that involve more easily available open source solutions. This will become more clear as we dive into the platform. Second thing we wanted was to consolidate best practices and tooling. So as I mentioned, all the microservices at our organization are based on Kubernetes, and which means we get free out-of-the-box support from our core platform and backend engineering teams. And this is a huge bonus, obviously. And then finally, we want to abstract as much of the low-level Kubernetes manifest, Terraform, et cetera, from the user as much as possible, while still making the platform customizable. And also worth mentioning that we want to maintain parity between offline experimentation platforms and online production environments. So the cluster should come up in the same exact way to avoid any surprises in terms of how things run between the two environments. So with that goal in mind, let's take a look at the overall architecture of how things look. So we're just going to focus on a couple of things highlighted here, and then I'll jump into each of the things one at a time to describe how they look. So first off, we have this thing called a custom cluster config, where the user essentially defines how they want the cluster to look, followed by a libraries block, where they just say, for the particular application that we want to run the Ray cluster, what Python packages, version, et cetera, we want installed on there. The base cluster config is this low-level sort of common cluster YAML. So this is actually just the Kubernetes manifest under the hood, which we want to abstract from the user because presumably it's not something you want to edit often. But if you do, you have the option to. So these configs and libraries are essentially just committed to GitHub. That's it. You put them on there, and Actions builds the image stacks for you, which are going to be installed in the cluster. And that's kind of where the user hands it off. Then we consume these three components together via Argo CD, which is kind of the main platform choice we made here, to then create a working Ray cluster CRD. So this combines all the three components and then applies it on a Kubernetes cluster to spin up a Ray cluster. So, compared to just applying a Ray cluster CRD via Helm or a Kubernetes apply, why did we choose Argo CD? So three key things that it gives us. One, Argo CD actually hooks up directly into the GitHub repository to track the cluster state and point to kind of a single source of truth for the cluster configs. So the manifest, whatever changes we make, libraries, those can all just be directly gotten from GitHub. It has a nice UI to track components, image tags, etc., which out of the box gives us pod logs, monitoring events, etc. And then finally, because it has all this history, you can actually roll back to previous image tags, previous versions of the Ray cluster app. Again, none of these things were actually something we had to build and just came out of the box. Okay, so with that, let's jump into each of these components and just look at a little bit at how they work. So this is the custom cluster config that the user has to specify. Pretty purposely simple and bare bones. You just have to specify which workers you'd like and how many of each. So this is just a resting state of what the cluster looks like when it's spun down. And then let's say you wanted to spin it up. So just add some replicas of each type. This is all you would do. Just add the number of replicas you want. That triggers this very simple workflow, which essentially shows you a diff between where you were and where it wants to be. So it's trying to add replicas to the CPU, replicas to the GPU. And again, worth noting that this diff is, again, not something we generate and is kind of inbuilt to Argo CD. So it tracks changes between the current state of the app, the desired state of the app, declaratively tries to apply it, and shows you the diff. We'll approve this. This is what the resting state of the cluster looks like on Argo CD. The new pods come up. This is what it would look like. So just a couple of seconds to kind of stare at this Argo CD UI. You can look at the pods. It's a nice UI. You can look at the history of the app, which image tags you use at which point, roll it back as needed, and then individually track the logs of each of these pods, Kubernetes events, whatever you need to. And then finally, just to close the loop on end-to-end automation of this, we talked about specifying the Python libraries we need. So just kind of a bare bones list of common things you might need. This triggers a GitHub Actions workflows, which just builds the Docker image for us. Shows you the tags, which are actually automatically applied to the Argo CD application, which for us is our Ray cluster. And so all you really need to do is approve and deploy it by hand in the GitHub UI. Yeah, so that's kind of the overview of the Ray cluster setup we have. And just to close the loop on this, we automated the whole process. Minimal custom tooling, still has a UI, and allows the user to customize it as much as possible. The next thing I'd like to spend a bit of time on is last mile data processing on Ray. So we've previously at this venue also heard about pipelines created in Spark that essentially creates features, puts them on S3 to use, where Ray essentially just reads the data and trains models on them. But there's kind of a shift now to actually push this last mile data processing to Rho, even at the cost of some efficiency. So Ray doesn't understand SQL. There's still kind of features missing. But even so, we found that moving this last mile processing was helpful. So what we essentially did is we did the massive joins in Spark and created this iceberg table, which forms the spine of our feature processing pipeline. So it then allows us to stream data into Ray, so things like one-hot encoding, binning of features, etc. And this is possible with an Iceberg connector on Ray data, which we actually contributed back to the community. And then the other thing we get for free, because we use Iceberg for this, is the ability to use things like DuckDB to perform ad hoc analyses on the data itself. So yeah, that's me. Hand it back to Jonathan.
Hey again. So I'm gonna close things out here, just give an overview of next steps for this platform. I alluded earlier, and the title actually mentions this, our overall goal here at Hinge, as far as this platform goes, is to drive down the time to production for existing and new solutions. compute orchestration and Ray platform that they've overviewed is one very critical part of this, but there are other elements of this that need to be addressed because ultimately putting ML into production is a composite problem, right? So to that effect, here are three focuses of the AI platform core team at Hinge moving forward. One is we want to take this Ray infrastructure and integrate it very smoothly and very cohesively with our feature store platform. We want to heavily tie things to Hinge's existing data platform, and enable such a functionality on top of that, such as automatic feature lookup for both training and serving. And at the same time, we want to invest in the ability to create feature endpoints, basically allowing developers to host data sets and batch predictions as if they were services themselves behind REST or gRPC endpoints. Secondly, as far as cluster management goes, we want to basically make them persistible and reproducible. That way, if an experiment or a model needs to be trained or created or updated in a certain way, we have the guarantee that we can reproduce that configuration end to end, so that we can retrain that model reliably and efficiently. On that note, the last part of here is general experiment management. We want to build out standardized approaches and tooling to basically capture the elements of the model development lifecycle. And with that, we plan to invest in by default lineage tracking for all models, as well as the features that they use, and then by extension any downstream models that might rely on this model's input as well. This will help us to ensure rapid prototyping and A/B testing in production, which we expect will be very valuable for the company moving forward. And that is all that we had for you so far. Thanks for stopping by, and we have lots of time for questions now.
Thank you. For Q&A, please use this microphone so your question will be recorded together with the talk. With that, any questions?
Great talk. So I had a question on that when you had to turn on the cluster, you have to manually change the replicas from 0 to whatever replicas you want. Why not rely on the auto scaling of Kubernetes?
Yeah, great question. So I will say this is just an instructive example, and you're absolutely right. Auto scaling is the right thing to do. Generally, though, and I think this was kind of the recommendation on the Ray page as well, that auto scaling is kind of in beta, so don't rely on it too much. But more and more, we found that it works quite well for our use cases, and we tend to do that.
Hi. Two quick questions. One for your feature store feature lookup. What are you planning on implementing? How are you planning on doing that? And two, for your model, like the top photo, how are you testing if that's working successfully, and actually how are you testing the success of that?
Yeah, absolutely. I can talk a little bit about that. I think so. As far as the automatic feature lookup part goes, that's in flux right now. As Hinge is growing very rapidly this year, there are a lot of underlying infrastructure changes that are happening at the same time. So it's a bit of a non-answer, but we're still figuring out the plans for that, and it'll be really heavily dependent on our data platform team, actually, which we're working really closely with. As far as ensuring that all our models, top photo included, sort of are doing the right thing and behaving as expected, we sort of all of our teams deploy very specific testing mechanisms to ensure before the model goes into production. And this is a combination of offline analysis as well as when we deploy, we collaborate really heavily with our back-end teams to make sure that, even if this model performed as we expected in an offline setting, we ultimately, if this is going to be part of our service mesh, it needs to make sure that the system, the overall architecture itself, can behave as we expect. Mm-hmm.
So I was wondering, what is the learning curve by converting from Spark ML to the Ray, and is there any suggestions or practices you want to share with us?
Yeah, another great question. So I think the learning curve was relatively flat, and a big part of that is just the modeling paradigm itself changed. So we went from non-deep learning to deep learning, which is kind of its own thing. We never tried to do that in Spark. Personally, I think PyTorch was much cleaner, easier with the array wrappers. The kind of big thing was just learning how to tune the array clusters. So when you have out of memory things, what's the best way to read data in, right? So it took a while to get to the iceberg solution. Heterogeneous cluster management is also something we never did before, so CPUs and GPUs together. Yeah, I would say on the order of 3 to 4 months, roughly.
Question over here.
Yeah.
Great talk. Thank you. In terms of observability and that experiment tracking piece, are you guys using like kind of the pre-made ML flow weights and biases systems, or are you doing that in-house? I was just curious because that wasn't on the diagram.
Yeah, for observability and kind of monitoring, we have Grafana and Prometheus out of the box, and then we use weights and biases for the ML stuff.
A question over here. I was wondering, how do you deal with like live traffic? So when you do a deployment, have you faced any issues with like split ray heads? How do you kind of deal with the new cluster being deployed?
So as far as serving live production traffic goes, we have a ray serve sort of like solution built on top of this baseline ray infrastructure. As far as like we haven't ever experienced any issues with ray itself in deployment. So I think most of our difficulty tends to come around around very basic things like knowing how to tune the like auto scaling parameters and so on and so forth. I don't know if that answers your question at all.
Thank you. So can you guys expand a little bit on the DocDB and share some of the learning you guys were using the...
Yeah, I think the big thing there was just, Iceberg makes all this nice metadata available. So quick things like, I don't know how many likes were sent by men versus women in a particular cluster over a certain date period. You would have had to spin up a Spark cluster in the past, or maybe use a data warehouse, which we still do for some of our heavy-duty queries. But just having DuckDB available as an option, Python native, you can quickly just spin it up, no need for resources, has just made certain things faster that were not the case before.
All right, thank you very much. Another round of applause for Dave and Jonathan. Thank you.
Thank you.